And you're welcome. You're learning from me. Good. I have your future in my hands. It's all completely fine. Okay. But I can't get the recording thing to stay up or down. That's good. And now this won't go away. Like some.
You can't make like the smallest one that you follow.
You can, but then it fights you, and it goes back to this because my computer doesn't like me very much, and I need a new computer. My other computer I have its smallest one, but it's so old that it moves at the speed of a snail, a really slow snail, like not the snail that could possibly pass the tortoise or something like that. The tortoise is slow, but I think a snail's slower than a tortoise, I would put. So, yeah, I agree wholeheartedly on that statement. I also liked when you could pull it, like, I want blue, and then I want red, and then I want green, and I can just, so now I just have this Harry Potter wand, which only gives me one color really quickly. And not even really quickly, I have to touch the marker thing to get the Harry Potter wand. It's a conundrum. All right. So we have talked about polynomials already. I actually used to teach the polynomial graph lesson first, because that would make sense. However, it was like a blank slate, and you were learning everything, and it was a lot of overwhelming information. Here, I do it where you learn factoring and solving first, so you've actually looked at graphs. You've kind of seen what a quadratic graph looks like, I hope, last year. You've seen what a cubic, you've seen what a quartic, a quintic looks like. We've talked about the constant being the y-intercept, right? We've talked about the constant being the possible factors, and we've talked about points of inflection already, where it does that S thing through it when there's 3 x-intercepts, or 5, or 6, or 5, or 7, or 9. And then it does the point of tangency where it hits it and it bounces if it's 2, or a little wider if it's 4. We put the 10 in, it got a little wider, right? But it still did the tangent thing. So you've seen all that. So actually, most of today is not new. You've actually seen it before. We're just solidifying it in a lesson. Okay? So, a polynomial function is a function whose equation can be written in p of x equals a n xn, a n minus 1, x n minus 1, etc., 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 where n are natural numbers, given the degree, and then all this information. The key thing about it is we'll go what polynomials are not below, which will be more helpful than what polynomials are with variables. Okay? So one of the first polynomials we can have is a constant function. So type into your calculator y equals 2. I will as well. We will teamwork. Oh no, I think it's going to... Oh, it does let it work. A Harry Potter one. And you might want to go zoom 6, just in case you have some crazy window sitting there. I don't know what it is. Yeah. So y equals 2 is a constant function. It means that for every x, my y is 2, right? Y equals 2 is also a horizontal line, correct? Because where does y equal 2 exist? On that line, all horizontal things. So y equal lines are actually horizontal lines, and x equal lines are actually vertical lines, correct? That's why the y-axis is x equals 0, and the x-axis is actually where y equals 0, so it's the equation y equals 0. So sometimes they'll say instead of reflected in the x-axis, they'll say reflected in the line y equals 0, because that is the x-axis. You've seen that happen on the handouts. Now, this is y equals 2, okay? What y values are on it? 2. What x values are on it? All of them. Infinite, correct? So if we look at this one, this would be x2, x to the 0, technically, which is the weirdest thing ever. So it would be degree 0. And what's its leading coefficient?
2.
And what's its constant? It's actually 2. It's still the same thing. Because anything to x to the power of 0 is the constant. It happens to be its leading coefficient as well. It's kind of weird. You don't see constants very often. We're just showing it to you because it is technically a polynomial. Yeah?
Why is it 2x to the 0 as opposed to x to the 0 plus 2?
Because the variable on it is x to the 0. So like if you don't have a, because anything to the power of 0 is 1, correct?
Yeah.
And every single number you have in a polynomial will have an x to something, correct? So down here I have x to the 4, x to the 3, x to the 2. This would be x to the 1. This would be 6x to the 0.
Okay, so if the x to the 0 is something else, then it wouldn't make sense because the 2 already has it.
On.
Okay.
Yeah. Okay, and we talked about this. The domain would be every number. So for this one, it would be x such that x and down to the reals in set notation. And my range would just be y such that y equals 2. Then we got into grade 10. Well, that was kind of in grade 10 too. In grade 10 we had linear functions. So this is 3x to the 1. And this would be 4x to the 0 technically, but I don't need to write that, correct? So what degree is this? What's the largest exponent? 1. It's a degree 1, linear or degree 1. And my leading coefficient is 3. And my constant is -4. Now type that one in. 3x minus 4. So it's discoing. It's just a really crazy disco. It's like at the disco when they're at the end and they're just like standing there looking weird, but they don't know what to do. I would imagine disco was in the when? 60s, 70s? Somewhere. I wasn't born yet. All you people who thinking I was not. I think it was in the 70s. Disco? We're going to pretend it was. You guys were not even close to being thought of at that time.
If you don't know, we don't.
No. You were born in 2003.
5.
Oh, I was going the wrong direction. Oh boy. I had it. I was going to say it, and then I went down. Because, yeah, my niece graduated in 2004. Born in 2004, graduated last year. That makes sense. 2005ers. It's okay. I finished university in 2006. It's fine. Next year's grad class was actually born when I finished university. Cool. I'm not old. So, disco, back to the old disco thing, that when I wasn't born then, because I'm not old. It's like they struck a pose at the end. Boom. Right? And if they disco, the x values are going on forever to the right and to the left, right? Like, look at my arms. If someone could visualize this on there, they'd be so happy. We're going out to the right and left forever. We agree? What about up and downsies? My Y's. We're going on forever. My arms were not going in the right direction. This arm was swirling. Anyways, they're going up and down forever, correct? So if they can go on forever to the right and the left, and they can go on forever up or down, then it's XER, YER, right? So whenever a graph can disco at the end, it's XER, YER, unless it's a word problem. Because word problems can restrict domains, correct, and ranges. Like if it was a time graph, let's say, I wouldn't go on for life. I would start at time equals 0 and carry on, correct? So when it's not a word problem, any discoing graph is XER, YER. Okay? And this is a discoing graph. So my domain would be XER, X such that X number the reals, and my range would be Y. That was grade 10. Little did you know that every single time you were given a linear equation, you could use no brain matter and write XER, YER, and you would have gotten every single domain range right in that equation, in that part. And then we got to grade 11, and we're like, hey, there's quadratics. Hello quadratics. What degree is this? 2, because my largest exponent is 2. What's my leading coefficient? 2, and my constant? 5. And remember my constant? When these are in step, I did nothing. I waved my Harry Potter wand. I think that's what's happening here. I think there's like, yeah, I think I might have waved my arm near it. Nope, I don't know what's going on. Anyways, cool. When you're in standard form, which means there's no brackets, do you see all these equations have no brackets? The constant is the y-intercept, but why? Other than Mrs. Lepp told me. Yeah.
Because everything else has an x attached to it, meaning it affects the x-axis. Because the constant's the only thing that doesn't have an x variable attached to it, or at least it's being multiplied by 1, because x to the power of 0 is just 1. It would only affect the y-axis because it's set equal to 1.
Yep, you're going by transformations. Exactly. Do you have another reasoning? Yeah.
I was just going to say, if we're looking for the y-intercept, x's are going to be 0,
Yes.
and it's not going to be affected by
These are both examples of answers on the diploma that would be sufficient. You use transformations. You said, well, there's no other things affecting my x. I'm moving it 5 up. Therefore, if it's on the x-axis, it's going to move it 5 up and make me have my 0, 0 become 0, 5. And you're saying, hey, when I hear y-intercept in my sleep, I instantly scream out x equals 0. Not like monsters, right? So you fill a 0 in here, boom, boom, and you all dream of y-intercepts, I know. So you put 0 in here, cancel, cancel, we get 5, right? Both would work. So that's why for all of these, my y-intercept is just a constant because either I can transform it vertically or these all become zeros. Boom, 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 when you plug in 0 for x, right? And you get your y. Okay, let's plug this one in. 2x squared plus 11x plus 5. So what's the only thing I can't really see right now? Your vertex, right? The minimum of the graph. So do I need to change everything to hundreds and negative hundreds? Because that would sufficiently make me see it. You're all like, it's funny. That's what people do. It's legitimate. It's scary.
I'd rather go to 10,000, but
You know, that's true. You know, when in Rome. Make it bigger. All right. So what do we only need to change? It is me. I don't know.
maybe it's your hair will be back into it.
Probably. Maybe.
Yes.
I have to wear ponytails. How can it pick up hair? Oh, I even moved the page. No, I think I deleted the page.
Oh, no.
Come on, back button. Yeah, be there. Yeah. You know how much I like the back button. It's my savior. Saving grace. Okay, so I forget what I was saying. All right, we only need to change the bottom, correct? So we go to our y minimum and change it. Not by bajillions, because I need it just a little bit lower. So I go to my window and I'm like, yeah, I don't need to change you. Yeah, you're fine. Okay, I'm going to make you negative 12, and then you're still good. Boom. Didn't have to viciously change it, correct? Now, it's going to the right and to the left. What kind of x values are there? Yeah, they're all there. Okay, what about my range? Greater than or equal to negative vertex. True. So we need to find the negative vertex. How do we get it? We're not completing the square, because that's grade 11 outcome. They don't make you do it in grade 12. You go. Second, I want to calculate something. Trace. And which one am I going to pick? 3, the minimum. Left bound. Somewhere on the left. Right bound. Somewhere on the right. And then it says guess. I don't know why it says guess. It makes you be like, 7. And then you press enter. Just kidding, it's not. So it's negative 10.125. Saddest thing is when people tell me it's greater than or equal to negative 2.75. That is the x, not the y, not helpful. So please don't do that. You might just do it because it's just a silly error and you're stressed during your test. It's the y. It's the y. It's the y. So it's negative 10.125. And then we go y here. You know what? I'm going to be a rebel. I'm going to do it in an interval because there's less room. And I've done some in the other one already. All right. So I'm going to go less than or equal to negative 10. Nope, it's greater, right? Here. Negative 10 point. Was it 125? I don't know. Yeah. To greater. So greater is infinity. Round bracket. And my domain?
Infinity. So
And you should put D's and R's in front of them, but I'm really squished. You probably are too. You have the same paper. You're welcome. All right. I want you to try cubic and quartic. And then here's the quintic. Go. So cubic is degree 3. And my leading coefficient is 1. And my constant is 3. Now, it does some like thing in the middle, but ultimately in the end it still does what at the end? Discos. And if it discos, what's my domain and range unless it's a word problem?
Negative infinity positive.
Yeah. It's going to go on for life upwards and downwards. It's going to go on for life right and left. So my domain and my range. Or negative infinity, positive infinity. Now x to the 4 is either going to make a wonky w or a wonky m. It could be like this sometimes. Sometimes it's like this. Still an m, because I could still write math with it. You'd just think I was weird or on a bus writing math or something. But it's w's or m's. And this one is a w, because just like a positive x squared opens up both arms, positive x4 is going to open up both arms, right? So it's going to make a w over an m. My degree is 4, my leading coefficient is 1, and my constant is 6. So when I type this one in, I get x to the 4 minus x. Oh my gosh, the struggle is real. There. I should have just deleted it. Try saving it. Minus 7x squared plus x plus 6. Okay. So I need to once again change my window to a little lower. So I can see the bottom, because I know it's going to make a W, so I know there's a bottom on it, right? Okay, my domain. Just like my domain of a quadratic, my domain of a quartic, it's still arms both up going out for life, right? So the domain is still XCR. Did you notice that all the domains are negative infinity to positive infinity? Yes, because polynomials go on for life outwards, both arms up or both arms down, or disc going out, right? So they're going to be XCR unless it's a word problem, so you have to watch yourself. The range is, you have to find the minimum. So second trace, minimum. So it's at negative 12.95. Square bracket, negative 12.95, comma, infinity. Why is it a square bracket? Sorry? It includes negative 12.95. There is a point on, like there's a coordinate on that negative 12, right? So if it was like an open dot and then you had a crazy polynomial graph, then it would be not equal to, and we'd have a round bracket. And then my domain is, I don't know why I'm switching it up. What is going on? Set notation is in my soul. I think that's fine. Okay. Now this one, this X5 graph, let's look at it. I gave it to you specifically because it's a little bit different. There's nothing on it. It just is this. Okay. It just curves through. It looks like it's a cubic function, actually, because a cubic function does a little S shape through it, correct? So if it was a cubic function and it went through, it would actually look more like this. Oh, it doesn't let me draw on this one now with the new board. Okay, if it was a cubic function, it would just kind of curve through quickly and go up. But because it's a degree 5, it kind of does this a little bit more and through. Makes it wider, because why? How many x-intercepts are there? There's 5 this time instead of 3. That's why it's a little wider. It would be actually x equals 0 multiplicity 5. So the only way a degree 5 can look like a cubic function is if all 5 x-intercepts are sitting on that one spot. So your point of inflection looks wider. Like if you look here, it actually looks kind of wonky. It looks wider. Like if I do this, why I didn't just do this in the first place, I'm not quite sure why I tried to draw it when I could have just put it on here. But whatever. Not the fastest letter. It makes it go through it. And it does the same thing. So people will say, well, how do I know if it's an x cubed or an x5? Well, they'll have to say determine the equation of a degree 5 function. Well, then if you know that this is a degree 5 and it looks like that, then there has to be 5 there. Like they have to let you know it's a degree 5 or a degree 3. They can't just be like, you can't be like, it looks a little wider there, so I think there's 5. Like, that's not going to happen, right? They're either going to say it's a degree 5 or a degree 3 function, and you're going to have a curve through there, and you're going to have to know there's 5. Or they might ask you to determine the equation of that. Well, the equation of that is I have technically an x-intercept at 0, so I could have a factor of x plus 0, let's say, and I have 5 of them. Well, that's the same thing as x to the 5, right? So we're going to get to learning how do we write equations to graphs as well. That's not today. We're just looking at graphs. So this one has a degree of 5, a leading coefficient of 1, and a constant of nothing. So if there isn't a constant, we've learned that it's a 0. We also learned that if we had to do synthetic division and there wasn't a constant, what would be my first step?
Factor of next.
Yes, factor out next, GCF. So if I gave you a synthetic division, or I asked you to solve, or I asked you to factor, and there was no constant, your very first step would be to take out an x so that you get a constant, and you've already knocked it down 1 degree, right? Okay, so what is and what is not a polynomial? Well, let's give some examples. The first one is x to the 5, x to the 1, and technically this is x to the 0. So as long as my exponents are whole numbers, it's a polynomial. Okay? So this one's x to the 5 whole number, x to the 1, x to the 0. And what are whole numbers? Whole numbers are the natural numbers plus the one with a whole, which is 0. Okay? So 0, 1, 2, 3, 4. The only difference between whole numbers and natural numbers is a 0. That's it. The number with a whole. Okay? So this one is a polynomial. Boom. This one's x squared, x to the negative 1, x to the 0. Is this a polynomial? No, because negative 1, it's not a whole number. So it's not a polynomial. Now why? We have to go back to grade 10. This one is 7x to the 0. This is 4x. This is 1 over x squared. People say 0, 1, 2. Boom, it's a polynomial.
1 over x squared is just x to the negative 2.
1 over x squared is just x to the negative 2. This is literally as bad as that. These are equivalent. So this is the same as x to the negative 2. Or 1, keep the 1 in the front, x to the negative 2. So when you want to move an exponent from the denominator to the numerator, you can move it by making the exponent negative. If you have a negative exponent in the numerator, you can move it to the bottom, making it positive. And you learned that in grade 10. You guys moved exponents around like crazy in one whole unit on exponents, exponent laws. Then we never really touched them in grade 10 or 11, which is weird. Okay, do a little bit of them, I guess. So this is no. Okay, this is x to the 4. This is x cubed. This is root 6. Root 6, people tell me, well, that's not an exponent. That's a whole number. There is no exponent on that. That is a constant, correct? So what is this exponent? X to the 0. So does this pass 4, 3, and 0? Yep. Grade 10 again. Grade 10 is used so much in grade 12, it's crazy. Most questions are either completed with grade 11 math or grade 10 math, and more often grade 10 than grade 11. So when people are like, oh, grade 10, you have to just, it'll come back. Reducing radicals, fractional exponents, negative exponents, changing radicals to fractional exponents. You guys did that in grade 10. Well, here we are again. Root x. Square root of x. What exponent is on x currently? 1. Yeah, someone's giving me the actual answer. There's a 1 on here. And what's the number in the index? 2. 2 is the little index, the little number up there. And all you were taught in grade 10 is to drop this baby underneath. So we get x 1 over 2. So it's x to the half, right? You're just taking that index and you're dropping it under the exponent. And these are equivalent. So root x is actually equivalent to x to the half. Do you agree? So I could rewrite this as y equals x to the half plus x to the 5 minus 7x to the 6. And by 5 is 6, good. Half, is that a whole number? No, that's actually a rational. So, no. Okay, if I expand this, I'm going to get x times x times x, which is x cubed. You also just did synthetic division. Do you see how I'm working backwards? Because it makes more sense, because you guys have done this already. You guys took a standard form equation and made it factored form, didn't you? Did that over and over and over. X cubed, x4, x5. We agree? So what is this? This is just, these are all standards. What is this? Just factored form. X minus 5 is one of them, x minus 7 is one of them, x plus 4 is one of them. What are the x-intercepts on this actual graph? 5, 7, and negative 4. So factored form gets you solutions, solving x-intercepts real fast, correct? But standard form, this form that we had up here, the 2 check marks, gets me the leading coefficient, so it'll tell me how we end on the right, which I will go over in a second, and it gets me my y-intercepts. So both forms are helpful depending on what you're looking for, right? Y-intercept's way easier with standard form, x-intercept's way easier with factored form. So this one's good. What about this one? X to the 6, x exponent, and x to the 0. Is that a polynomial? No, when your x is in the exponent, it's called an exponential function, which is what we're going to deal with this year. This is exponential, not polynomial. So no. Okay, then we're going to flip over. Yeah. So this chart below goes through kind of a little bit of different things quickly so you didn't have to write them. So the chart below shows the characteristics of polynomial functions with positive leading coefficients up to degree 5. How would the graph change if we have leading coefficients that are negative? So here we have degree 0. It has a positive leading it's just 3. So it's horizontal. This one has a positive leading coefficient of positive 2. Thanks, board. I'm obviously doing something wrong because we figured out the hair problem, but I don't get what's going on. This one is a positive leading coefficient. This one has a positive leading coefficient, 2x squared minus 3. This one has a positive leading coefficient. This one has a positive leading coefficient. This one has a positive leading coefficient. We agree? Let's go over a little bit of facts. We've already discussed these before. Degree 1 is XER, YER. We've discussed that. We also said that it can have one x-intercept. It has to have one. Minimum 1, maximum 1, because it's degree 1. It has to cross through at some point, correct? Then we talked about quadratics last year a lot. The domain is still XER. Your range is greater than or equal to or less than or equal to, depending on if it's concave up or concave down. But it has, this one has 2 x-intercepts. So what are the possible numbers? 0, because it could be completely above or below, because the arms are in the same direction. 2 is my max because of the degree. And then we have every varying level in between. That's what you always do. So your lowest is based on if it's even or odd. If it's even, it's going to be 0, minimum x-intercept. And your maximum is based on the degree. So if it's degree 2, we have a maximum of 2 and a minimum of 0 because it's an even degree. And then we can also have 1 in between, because that's where it's tangent on the x-axis. Now, degree 3 cubic functions have possible number of x-intercepts of 1, 2, or 3. Correct? It has to have 1 because it's discoing. At some point, it's going to cross through. It could have 2 or 3. 1 would look like this. Could go like that. That would be 1. 2 would be where it has to be, one of them has to be tangent, so it touches and bounces. That would be 2. And then 3 would be just your generic runs through. Right? 1, 2, or 3. Degree 4 can have 0, 1, 2, 3, or 4. Why can it have 0? Your arms are in the same direction. So 0 could look like this. The whole thing's above, right? Or if it's an M, the whole thing's below. 1, it would have to like touch and then do the rest up. This would be 1. 2, it would have to be like one of them going through. 3, you'd have to have a tangent, go through and then bounce. And then 4 would be like whole W goes through, right? Yeah.
Could 2 also be just 2 tangent points?
Yep. Bounce and bounce. Yep, absolutely. So he was asking to be this. Yep. Like a symmetrical W. Absolutely. And then degree 5, you can have 1, you can't have 0 because this goes. At some point it's going to have to cross through, right? And then it maxes out at 5 because that's the degree, and then you can have the varying level in between. So 1 would be, could be like this. 2. I suck at drawing these, just so you know that needs to be symmetrical. 3 would be like a cubic, and then like another bounce here. 4, like there's varying levels of what you can do. 4 would be like That's not 4. That's 3. 4 would be like meow, 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 meow. 1, 2, 3, 4. Yeah. And then 5 is just like the answer. What do we notice about the right arm on all of these? It goes up. Your positive leading coefficient tells you how it ends on the right, just so you know. So if it's a positive leading coefficient, it ends up on the right. See, up on the right, up on the right, up on the right, up on the right, up on the right. What tells you how it ends on the left? The degree. The degree totally tells you how it ends on the left. Because if it's an even degree, they're the same direction. If it's an odd degree, they disco. We agree? So this one's an odd degree. I know because it's a positive leading coefficient, it ends up on the right, but I know it ends down on the left because it has to disco. This is a positive leading coefficient, so it ends up on the right, but I know it has to end up on the left because it's degree 2, and degree 2's end in the same direction. They're even degrees. This one's a degree 3. I know positive leading coefficient ends up on the right. I know it's going to have to disco, so I know it's going to have to end down on the left because it's an odd function. An even function is a degree 4. I know it's positive coefficient, so it ends up on the right, but it ends up on the left as well because even ends in the same direction, and odd discos. So odd here, positive leading coefficient, has to end down because it's going to disco, right? So positive leading coefficient ends up on right. Even degree. Arms bend in same direction. Odd degree. Disco. So you knew a lot of this before even coming into this because of looking at the factor form graphs, I believe, like, and looking at the standard graphs. So there's just going to be a little bit to work on this for today, finishing the rest of it tomorrow, and then just graphs and we're done. Graph equations, and we're done this unit. Move on to break. I will hand out the hand-in, but it's only going to be due for Monday of next week. Right? I want to hand it out because a lot of it is graphs, and until you get the graphs down, the hand-in, you don't know what you can do and can't do, so I'm just handing it again. Yeah. And Tuesday. Good call. All of you have to be here on Monday handing in your hand-in. It's be real awkward because I'm not going to be here. I'm not sure how it slides under the door. Outside. I don't think you can. That's a you problem, so it sounds like. Just kidding. Good call. Tuesday. All right. So, page. Check that. 114. Number 1. That's just telling you if it's polynomial or not. 2. C, E, F. I'll just say C. 3. 4, B, C, D.